So I have this situation here where I have 3 ice skaters all in a row. And there's the one in the lead that is skater number 1. And there's the one in the middle is skater number 2, and the one at the trailing is skater number 3. And they're skating along in a line here, and they have their hands on each other's shoulders going along. So what we want to do is to draw a free body diagram for the skater in the middle. And the important point here, and the point of a lot of these problems, is to realize that when I draw a free body diagram, I draw only those forces that act on the object that I'm drawing the free body diagram for. Now in this case, I'm drawing a free body diagram for the person in the middle. So while it's true that the person in the middle exerts a force forward on skater number 1 and a force backward on skater number 3, those forces don't go on the free body diagram. I only want to draw the forces that act on the skater in the middle. So here I go, a box represents the skater in the middle, and the skater in the middle, skater number 2, has a weight directed downward, mg. Maybe I should say m2g to specify that I'm talking about the skater in the middle. And the skater in the middle has a normal force that acts upward, the ice pushing upward against the middle skater. I call that n. Maybe I should call it n2. It turns out not to matter for the problem. Now, the skater in the middle has a skater in front, skater 1, and a skater in back, skater 3. It's probably easier to see that skater 3 is pushing the skater in the middle from behind. That means that the force that skater 3 exerts on skater 2 is directed to the right. So on my free body diagram, I put the force of skater 3 directed to the right. Now the force of skater 1 is the tricky bit of this, I think. Skater 2, the skater in the middle, is pushing forward on skater number 1, or perhaps pulling skater number 1 backwards. I don't actually know. But that's not the point of the problem. The point of the problem is, what is the force that's acting on skater number 2, the skater in the middle? That force is the force due to skater number 1, and it has to be directed to the left simply by virtue of the fact that skater number 1 is to the right of skater number 2. So on my free body diagram, I've drawn the force exerted by skater number 1 on skater number 2 as Fs1 directed to the left. Now I have sort of a classic situation here where this girl is standing on a sofa, and I want to understand about the action-reaction forces between the girl and the sofa. Newton's third law of action-reaction says that when two objects interact, the one with the other, in this case the girl and the sofa, one object exerts an equal and opposite force on the other. These two forces are of the same nature. Sometimes in this particular question, students make the mistake of thinking that the action force is the weight of the girl on the sofa and the reaction force is the sofa pushing upward. Those two forces have different nature. The weight of the girl is the gravitational force of the earth on the girl. It's got nothing to do with the sofa. So what I'm looking for in this action-reaction is a pair of forces that have the same nature, that is, they're the same kind of force, that are equal in magnitude and point in opposite directions. Now to see that, I'm going to draw a free body diagram for the girl, and curious enough, I'm also going to draw a free body diagram for the sofa. The free body diagram for the girl is easy. The girl has weight directed downward, and there's a normal force exerted upward on the girl that I call the normal force on the girl. Very, very simple free body diagram. Just a girl standing. Doesn't matter if she's standing on a sofa or on the ice or on the ground. There's that normal force of contact, in this case directed upward. Things get curious when I draw the free body diagram for the sofa. What are the forces that act on the sofa? Well, certainly the sofa has weight, so I've drawn capital mg downward, presuming that the sofa is more massive than the girl is. And I've drawn the normal force exerted upward on the sofa by the floor. Now call that NS, directed upward. But what other forces does the sofa feel? Well, sofa doesn't feel anything. Sofa is an inanimate object. For a moment, let's put ourselves in the position of the sofa. Let's have a girl standing on another person who maybe is on all fours there, like some sort of not very impressive cheerleader pyramid. The sofa underneath feels the girl pushing down on the sofa, just as you would feel if you were on your all fours with the girl standing on your back. That force is sometimes mistaken for the weight of the girl, because very often that force is the weight of the girl. Very often, not always. If there were any acceleration vertically, for example, if, very strangely, this sofa were on an elevator and accelerating upward or accelerating downward, then the normal force that the girl exerts on the sofa would not be equal to the girl's weight. The girl would seem heavier or lighter depending on the acceleration of the elevator. So here on my free body diagram for the sofa, I'm going to draw the normal force of the girl acting downward on the sofa. That's the action-reaction pair. The sofa pushes upward on the girl pushes downward on the sofa. This one annoys me a little bit because for some reason in this problem they throw in the little added goofiness that the car is moving to the left. When I'm in the classroom teaching physics, I almost always start standing on the left side of the board, which means I'm going to draw most of my physics going off to the right. This car is going to the left. So I'm going to draw a free body diagram for the car on the road as the car, in principle, skids to a stop. I can tell by how I've drawn my diagram here, it looks like maybe the car is going a little bit downhill. It's not going downhill. Let's assume that that is a level road. I should have fixed that in post, as they say, but what are you going to do? So here's the car, and it's skidding to a stop. Free body diagram for the car. Does the car have weight? Yes. Directed downward, mg. Any surfaces in contact? Yeah, the car is in contact with the road, so there's a normal force directed upward. Is there friction? Yes. This is how the car stops. The car stops because there's a force of kinetic friction in the opposite the direction the car is moving. So I've drawn a friction force off to the right. But this question is not about what is the free body diagram for the car. I'm simply using the free body diagram of the car to respond to the question. The question is, what are the action-reaction pairs? First of all, how many are there? And what are they? Well, here, it's just like the girl on the sofa. The ground pushes upward on the car pushes downward on the ground. So if I were to draw a free body diagram for the entire Earth, I would draw a vector normal force directed downward, whatever the heck that means in the context of the entire spherical Earth. But a normal force on the Earth downward. That is one of the action-reaction pairs happening here. The Earth pushes upward on the car pushes downward on the Earth with an equal and opposite force. It's not the only action-reaction pair that's happening here, however, because there is a friction force that the Earth exerts on the car backward, and by backward I mean opposite the direction of motion. In this diagram I mean directed to the right. That force of friction is exerted by the Earth on the car. We never even consider it, think about it, and it's difficult to visualize. But there is a force of friction that the car exerts forward, that is directed to the left in this diagram, on the ground. That's an action-reaction pair. When the Earth exerts a friction force on the car to the right, the car exerts a friction force on the ground to the left. In order to visualize it, imagine instead of skidding to a stop on asphalt, that the car skid to a stop on an enormous carpet. What we would see would happen is that as the ground exerted a friction force backward on the car would exert a friction force forward that would bunch up all the carpeting underneath. We don't often consider that forward force. Nevertheless, according to Newton's third law, action, reaction. Now I have this problem involving a squid. And for me, on a personal note, it doesn't matter what happens next because I have done an amazing job at drawing a squid, head of the class. But nevertheless, I've got a little bit of physics going on here because the squid propels itself forward by expelling water in the opposite direction. This is the same principle that propels a rocket ship. A rocket ship burns rocket fuel and expels it out the throttle nozzle at the end of the rocket. The exhaust gases go one way and the rocket goes the other. A very foolish idea would be to imagine that a rocket ascends from the launch pad because it pushes on the ground. This is not the case. A rocket in empty space with nothing around it, no gravity, no planets, nothing. You turn on the rocket motor, the rocket exhaust goes one way and the rocket goes the other. And I've drawn that here with my squid. My squid is going to accelerate in the direction the squid intends to go. I've called that the acceleration of the squid, AS. And it does that by expelling water in the opposite direction. So I have a vector here that says AW, the acceleration of the water. Notice, I did not draw those two vectors equal in length. In fact, I've drawn the acceleration of the water as a larger vector. The reason why is that Newton's third law is not a law that says that there are equal and opposite accelerations. It's a law that says that there are equal and opposite forces. So Newton's third law applied to this situation is that the squid experiences a force in its direction of motion by exerting a force on water opposite the direction of its motion. Those two forces, an action-reaction pair, are the cause of the motion. In this case, the force that would be exerted on the squid can be calculated by taking the mass of the squid and multiplying by the acceleration of the squid. The force exerted on the water is the mass of the water times the acceleration of the water, but these two numbers are going to work out to be exactly the same. They're opposite in direction, so I might say that one force is positive and the other force is negative. Nevertheless, the amount of force, the number of newtons, is equal. So I can say the force exerted on the squid is equal to the force exerted on the water. So the mass of the squid multiplied by the acceleration of the squid is equal to the mass of the water multiplied by the acceleration of the water. The forces are equal and opposite. The accelerations are in proportion to the mass.